ski. Which,
I want 1.4.
yeah, man, 1, 2, 4.
We'll jibber jabber about it.
Yeah, we'll have a little chit chat. Oh, that's a good one.
Matt, you can talk. You talk.
No.
All right.
Dad.
So
What do you think?
to start, Boyd, what I'm going to notice is that
They're like, you're doing it right.
if I have an exponent of an exponent, that means multiplication, right?
Wait, what do you mean exponent? Oh,
Like if I have x to the a to the b, that's the same as x to the a times b, right?
yeah.
So I'm going to use that property here to rewrite that as e to the x squared instead of e to the 2x. Is that okay? And now I'm going to notice this looks a lot like a quadratic. So I'm going to just replace those e to the x's with y's. And what I'm left with now is a quadratic equation. So I could solve this either by factoring or using the quadratic formula. Do you have a preference on which one you do?
I'd rather do quadratic in this case.
The formula?
Yeah.
Nah, that's what I would have chosen.
I would have chosen that too.
Since the leading coefficient isn't 1, it's kind of a hassle.
If I had
All right. 5 squared is 25, and then minus 4 times 2 times negative 3 is minus a negative 24. 25 plus 24 is 49. The square root of 49 is 7. So if I do negative 5 plus 7, that's going to be 2 over 4, which reduces down to 1/2. And if I did negative 5 minus 7, that's negative 12. Divided by 4 is negative 3. Oops. Those are not, nope. But that's the solution for y, right? What are we trying to solve for? X. So what I'm going to do is I'm going to say, okay, let's put back the e to the x then. So we have these two equations then, right? How do I cancel out the e, the exponent base of e?
So, natural log.
I'm going to do the natural log to both sides. Excellent. Now, the natural log of 1/2 is just some decimal. That's fine. But I can't do the log of a negative number. So that part just, that's undefined. So this should be my only answer here. And because I'm solving an exponential equation, not a logarithmic, any answer I get is going to be okay. I don't have to worry about extraneouses if what I'm solving is an exponential equation. That's what I started with, right? So that should be good. I don't remember on the answer. I guess it's an even one anyway, so it doesn't really matter. I'm perfectly fine with you leaving it as like just a natural log of 1/2. Or you could type it into your calculator and get the kooky decimal. It's going to be some negative number, but that's fine. There you go. If you want the decimal, that's cool. And just so you can see, if I plug that back in, my equation, so I do 2 times the natural log of e to the 2x, and then plus 5 times the natural log of e to the x minus 3, and instead of x, I put in that number that we just came up with. I do indeed get the 0 I'm supposed to, so I know that answer is correct. Are you happy with what we did there, Boyd?
I am overjoyed.
Great. That is a heck of a. We had a great session there, Dwan. Certainly, it's the easiest question I'll have to answer all day. What else you guys got? Anything else you want to talk about?
Is that in your mind, Lindy?
I finished the homework and I'm up to the next one. So,
Boyd, you got one more?
Like one,
Sure.
last one, 1.5.
125? Yeah, no problem.
the last one. Numbers.
All right. So this is a logistic equation, but that's no big deal. So what I would do here is I would just think about this as like 200 over 1. And then I'm just going to cross multiply. And just turn that into a exponential equation. To solve this, I'm just going to then divide by the 200. So I'm going to reduce the 500 divided by 200, just make it 5 over 2. And then we'll subtract 1 from both sides. Five over 2 is 2.5. When I subtract 1 from that, I just get 1.5. Just going to raise the fraction 3 over 2. And then we'll divide both sides by 25. That's the same thing as multiplying by 1 over 25. So I'll write that as 3 over 50. Again, you would be fine converting these things into decimals, Boyd. There's no reason that you need to keep fractions other than, honestly, it's easier for me to just hang on to the fraction than it is to make it decimals. But if you're doing this just with your calculator or whatever, no big deal. Next, I need to get rid of that exponent base e. What do I use? Natural log. That's good. And my last step would just be dividing by the 0.03, or the 0.3. And I like to write it as like multiplying by the reciprocal, just so I don't get confused about whether that dividing is happening inside the log or outside the log. So I just like to write it that way. I think it's clearer to myself to see what's going on. But that ought to do it. So negative 1937, or I'm sorry, not 937. Is that one was an odd one, right? Let's check the answers. Make sure that there's no mistake there. This was 25. Yeah, that's good. That rounds to what we got. Cool beans.
What was the answer again?
Negative 938. I think I rounded up. Yeah. Oh, excuse me.
Dude, it's not a ball anymore, it's a portable TV. Are you gonna break it? You just shoved it in.
All righty.
And boy. And boy, yeah. Still one eye.
right, today we're going to be talking about the mathematics of finance, and we're going to be looking at 3 different models here that we'll use. Well, today at least 3 different models. So we'll talk about simple interest, compound interest, and then continuously compounding interest. All right. So when we say simple interest, what we're talking about is a situation where you're only going to earn interest on the original amount invested. You don't earn interest on any of your earnings. It's just that initial investment that earns the interest. The equation here for calculating simple interest is FV is equal to PV times 1 plus RN over 100. Where FV is the future value. That's the value of the investment at the end of the investment period. PV is the present value, or the original amount invested. R is the interest rate per year, that's written as a percentage. And N is the number of years in your investment period. So, for example, that's not what I wanted to pick. Excuse me. I'm in the wrong spot. That's the one I want. So let's say we invest 2,000 big ones at 6% interest. How much money do we have in the account after 3 years? We should probably say at a simple interest rate of 6%. Okay. So since we know it's simple interest, because it stated it in the problem, we know we're going to be using this equation. What are we going to be solving for? FV, PV, R, or N? FV, how do you know that?
After 3 years.
Yeah, it's telling us that we want to be looking at what's the thing worth after 3 years. Great. So what's going to go in for the present value?
2,000.
Good. What's going to go in for the R?
6.
Okay. And what's going to go in for N? The 3. You did say that. You did. So I bang that all through my calculator, and I get 2,360. I didn't really use my calculator. Well, I just 6% of 1,000 is 180, or is, I'm sorry, over 3 years is 180, and we're doing it twice, so it's 360. I just added to
Do a
the.
little,
Okay, I can never mind all day long. That's no big deal. Okay. So that's the value of the account. How much interest was actually earned? How much interest was earned? 360, right? 2,000 is what we started with. That's the same. That was our money already. We really just earned $360 just by parking our $2,000 someplace for a couple of years, which is, it's all right.
It's friendly. It's all right.
I mean, I kind of stinks having my $2,000 all tied up and not being able to use it on anything, but
Yeah, I only get $360, but
in all reality, like, nobody is doing simple interest. If you invest your money, or you put it in the bank, or you invest in the, like an annuity or some, whatever, nobody's paying simple interest. So they're going to probably be using some kind of compound interest. So the compound interest formula is FV is equal to PV times the quantity 1 plus R over 100K to the KN. Well, FV is still future value, PV is still present value, R is still the interest rate as a percentage. K is going to be the number of compounding periods per year. So like, if you have a savings account, typically I think most banks compound things quarterly. So you get like 4 times where the interest is paid in over the course of the year. Some investments compound monthly, some are, some might be weekly or daily. Just kind of depends on the terms of your that you're working with. So the power here of the compound interest formula is that your interest that you're earning on the account also then earns interest once it's paid. So like once you've earned your interest, the next time we calculate the interest, the total in your account is being used as the base value rather than just the initial investment. And you might think like that doesn't seem like it's going to make a big difference. And over the short term, you're right. But over the long term, boy howdy, it makes a big difference. All right. So here's the situation. It says you invest $2,000 at a 6% interest rate compounded annually. How much total money do you have in the account after 3 years? How much did you gain in interest? So this is almost the identical situation as the previous problem, right? What one word here indicates the difference? Yeah, that tells us that we're going to be using the compound interest formula to do this. What are we interested in here? Yeah, so after 3 years, we're going to be doing future value. Okay, what's the present value? Still 2,000. What's our interest rate? 6. What is our years?
the K a constant?
No.
Is that would
The-
that just be 1 because it's compounded annually?
Yeah, so the annually is telling us that K is 1. Yeah, that's right. So K is most often expressed in words. So you actually have to read the problem. So I do that, and I punch that through my calculator. That's what I get. How much interest did I earn then? 382 and a couple of pennies. Yeah. Notice that not a big difference from compound to simple here over the course of 3 years, right?
Yeah.
So what did it come out to? About 22 bucks?
I complain about that.
I mean, 22 bucks is 22 bucks, right? Let's say instead of doing it over 3 years, let's say we did it over 100 years.
Oh, yeah, that'd be large.
So we'll let me punch this through and just kind of illustrate to you the big difference, yeah, that the compound interest is going to make. So 14,000 on simple interest.
Yeesh.
So 14 grand versus $678,604.
So I probably did that one.
Yeah, right?
Yeah.
Like just a little bit more money doing it that way.
I would probably do that.
Yeah, there's probably the question would be the interesting question, at least to me, is at what year did I earn $14,000 in interest? There's probably at least 1 year in there where I earned more money in interest than I would have from the entire thing. You know, actually that's really only $12,000 in interest here, but I bet there's a year in here where I earned at least multiple years anyways, but there's probably some point where I started earning at least $12,000 in interest.
Would not be complaining there.
Yeah, that's
Like $1 billion.
that's a pretty good deal, right?
It's a billionaire.
Well, this is one of the reasons why once you're rich, it's easier to stay rich
Yeah.
because like you can earn a lot of money just by parking a big chunk of cash somewhere and just collecting interest.
Yeah.
That's what Bloom does. That's why he has a
Blue has like $1 trillion.
He doesn't even use a bank bill.
It's
He
all
doesn't
from the
believe in
cartel.
Oh, where do I keep all my money?
What in his back pocket?
Blue, aren't you a cartel leader?
Bloom shot my parents. Wow.
I got in the way of the deal. They wouldn't pay up.
So just as an FYI, when we talk about the K is again almost always going to be given to you in words inside of the story problem. So if we say annually, that means K is 1, semi-annually, K is 2, quarterly, K is 4, monthly, K is 12, weekly, K is 52, don't worry about that, like one extra day. Daily, K is 365, don't worry about any leap years.
So you are collecting interest for daily, whatever. Do you get screwed by the leap year, or does that help you?
Well, for our purposes, we're not going to worry about the leap
Yeah,
year.
like,
Here's in the grand scheme of things, is not going to make much of a difference.
no, it's just,
Because what's happening is in a daily situation, you're not getting paid interest like the whole interest rate 365 times. You're getting each day you're getting 1/365th of your interest paid in. Now that makes a little bit of a difference because that 365th is then compounded when you do the next calculation.
Yeah.
We're going to do an example here where everything stays constant except for that value of K.
All right.
And you can see the kind of difference that the number of compounds per year makes. To see if we see it's like little deal, medium deal, or big deal.
you kind of just understand most of
You just write this stuff?
Not really.
You just forget it.
No, I understand.
What's up, Boyd?
Do you think you could go for one more homework question?
Yes, but let's wait till I finish with this stuff. I'd be happy to do another one. no big deal. I just don't want to like change gears too many times. Yeah, you know what I mean? But yeah, we can for sure do another one. All right, so here it says Gina invests $800 in a 7% annual interest rate account. How much money will the account have in 5 years if the interest is compounded annually, semi-annually, quarterly, monthly, weekly, daily, etc.? So I'm not going to write out anything for this. I'm going to do it all just on the calculator, and we're just going to update the value of K each time. Is everybody good with that? Just so that it's not like, it's kind of a lot of writing. So I have my present value is 800. Then I have 1 plus, and then my interest rate is 7 over 100. Oops. And I'll write times 1 here, even though I don't really need to write it there, but I'm going to be updating the whole times. And then I'm going to do the number of years first and then times K at the end. So it just makes it easier to update it if I don't have the long number first. So annually, I got $1,122. Semi-annually, so I'll just update that and change that 1 to a 2. $6 is all the difference it made going from annually to semi-annually. But hey, $6 is $6, right?
You could use that to buy something.
Yeah, right. Quarterly, so I'll change that 2 to a 4. Let's see what difference that made. Like $3. Yeah, I know. It was like $2.50, okay? Like I get that there were some pennies there. We're just ballparking. Okay? So like went up another $3 monthly, so that's 12.
Nice little 12.
So I'll update that.
Hey, $3.
Yeah, another $3. What do you notice? It's less and less impactful each time, right?
Yeah, but I mean,
Go to 52 here. Yeah, well, it's certainly going to help, right?
yeah.
It's some deal, but,
Well, we made
and here, it was
cents.
like a little less than $1
Yeah,
going from monthly to weekly.
made some cents.
Yeah. And then we'll go 365 it.
Oh, okay, we made 3 cents.
Yeah, like 30 cents. A quarter and a nickel.
Yep.
Some silver. So the point of this homework or this exercise is just to show you that, yeah, the number of compounds per year makes a little bit of a difference, but not a tremendous difference, right? Like the bigger issue is going to be things like the interest rate, how long something's invested for, how much principal you're putting down. Those are things that'll have like a much, much bigger impact on your investment over time. Yeah, Kate.
Which one do you have?
Well, I think that most, like, if you're doing any, like, investing in a savings account or whatever, I think most of that stuff is paid quarterly. If you have, like, a mutual fund, I think that interest might be, I think all that stuff is updated daily through the stock market
Yeah, stock.
because it's not actually like, it's all like a conglomeration of stocks and a mutual fund. That's where most of my investment is. But if you have like a loan on a car or something, I think the interest on those loans are probably monthly.
Yeah, they are.
Or if you bought a house or something, I think the interest on that is all
Where is that right now?
monthly. Yes, sir.
How is APR?
I will actually talk about APRs here, but not today. So I will answer that question, but I'm just going to let it happen naturally when we get to it. But that is something we will talk about, but I don't want to do it today because I want to do this stuff first, kind of, you know what I mean? As like a little bit more foundation. Okay, slightly different question here. It says Mara has $1,000 and places it into a savings account with a 6% annual interest compounded monthly. How long will it take before Mara has $4,000?
Oh, so we're looking for
Yeah, good.
1,000.
So again, we know it's because of the word compounded. We know we're doing the compound interest formula. But yeah, this time we're solving for n. So what's our FV then?
4,000.
Good. And our PV?
1,000.
Good. And our R?
6.
And our K?
12.
12.
All right. So to solve for this, what are we going to have to do? After this example, go to lunch. Cool?
Yeah. Divide by 1,000.
Divide by 1,000 first. Great. And I'm actually going to do this in my calculator and just turn that into a decimal. And I'm going to do the 100 times 12 in my head so I don't have to use like a bunch of parentheses.
Shoulders and stuff like this.
Okay. I don't really need that parenthesis there. Okay, now what?
We're gonna take second divided by 1.05.
Not divide.
The log of
I'm going to do log base 1.005. So those cancel out. So I then divide both sides by 12, and that ought to be my answer.
I'm just wondering.
So we do math, and then we do
1 minute, guys.
log base. Thanks, Sadeki.
Guys, let him finish before you go.
Yeah, guys.
You're such a problem.
So about 23.2 years.
let them cook, guys. Hold up.
What shift is it? What happened?
Wow. What do you mean what happened?
Okay.
Nothing happened.
You guys, that's it. Go ahead. You too. You're cool. Come on in. All right. It's none of your business where he was. What are you, his mother? Oh, it's got a weird looking mom. She's young though, at least.
Yes, sir.
All right, here we go. Gwen has $600 to place in a savings account. What annual interest rate would she need, compounded weekly, if she wanted to have at least $1,500 in 10 years?
52. Yeah.
So again,
Well,
we hear the word compounded in there.
me?
Oh.
So we know we have that, right? What parameter are we solving for?
You're solving for
Yep. So the annual interest rate is what we're solving for. So we're looking for R. So we need to fill in the other values. What should our future value be?
1,000.
Excellent. And the present value? Great. And then R is our variable. What's our K?
52.
52, because it said compounded weekly. That's good. And then our N is 10. Great. Okay. So to solve this, what are we going to need to do?
You have to divide by
600, right? So if I do that, I reduce this down to 5/2, I think. Okay. Now I got to get rid of that exponent of 520. How do I do that?
You gotta do the log,
No.
you gotta do the ln thing.
No. Because I'm not trying to cancel the exponent base, right? That's got the variable in it, not a reciprocal.
Oh, you lost me.
Well, if that was just a 2, how would I get rid of an exponent of 2? A square root. So what kind of root am I going to use to get rid of an exponent of 520? 520th root. Then we're just going to subtract the 1. And then multiply through by 5,200. And that should be our value for R. Now remember, this is going to be an interest rate as a percentage. So let's type this in. 5,200 times -1 plus 520, and then to make that a root, I press math and choose option 5. So that made the 520 root. You see how it made it a up there in the index for me? That's how I have to do that. Now I get 9.17. So we need at least 9.17% interest. So just to summarize here, if we want a future value from a compound interest, there's nothing really to do, right? We just plug the numbers into the calculator, press enter, there's no algebra involved. If I want to solve for the number of years, what I end up having to do is I have to use a logarithm at some point, right? If I want to solve for an interest rate, what I end up having to do is use a radical at some point. So that's a nice little summary there to remember. Okay. The last idea here for today, I want to talk about the continuously compounding interest. So that formula FV is equal to PV times e to the NR over 100. PV is still present value, FV still future value, R still the interest rate, N still the time. E is that number, right? That like 2.78, yada, 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 yada. Well, how did we arrive at this formula? Like, why is there an E in there? So remember back when we defined E, that, oops, I should say, we said this, right? It was part of our definition of E. So if I say compounded continuously, that implies the number of compounds should be infinite, right? That at like every instant that's happening, faster than every second, every 100th second, every microsecond, every nanosecond, every instant, right? Infinitely many compounds going on. So if I take my compound interest formula. And I do a little rearranging. And if we say let x equal 100k over r, I can see that this piece is going to turn into like 1 over x, right? And what I need to do is I need to find a way to rewrite this n times k so that it has a 100k over r in the exponent. So I'm just going to multiply that by the k by 100 over r. So then I have to multiply the n by r over 100 so that the 100s cancel and the r's cancel, and I'm really just have nk in that exponent. You see how I did that? So this now is just going to turn into an x. And that's what I need because this is just e. So when we let that become infinite, that piece just goes down to e, and there's our formula. So this is really just the compound interest formula allowing infinitely many compounds a year. That's all that's happened there. Dwan? Yeah, so I had k times n, right? And I needed to make inside of it one of those. So I just multiplied that by like 100 r and then divided by 100 over r, or 100 r. And then I just rearranged this multiplication. So I had k times 100 over r. So I took like this, and that, and put it together. And then the other stuff, nr over 100, all went together into the other group. Does that make more sense? So I just multiplied it by 1 so that the symbols were in the right place so I could make the substitution I needed to make, right? Like, because I knew I was trying to get that 1 plus 1 over x to the x. That was my key that I was able to like know how to do that rearrangement, is I needed the x in the exponent. So I just put the stuff in there that I needed and then divided the stuff that I put in back out, and it just took care of itself. Does that feel okay? Okay, let's run through a couple of examples using this formula, and we're going to be done for today. Oops. How's your windshield, Bloom? Does it have a golf ball shaped hole in it?
Yeah, just a little bit. Right in the middle.
How did that happen?
Did you read my message, Blue?
Yeah, dude, you wrote
That was a terrorist attack. I believe the next spot is your house.
All right.
Yeah, Matt was behind all this.
So Jack invests $800 into savings account with a 5% annual interest rate compounded continuously. As soon as I see continuously, we're going to use the continuously compounding formula. How long will it take for Jack to have $500 in interest? What are we solving for here? Which parameter? Great, because it says how long. So the future value should be?
We want it to be 500. Or no, not 1,300.
1,300. Great. How'd you get 1,300?
Our starting plus what we want to have in interest.
Good. And the present value?
800.
800. And is our variable, and R is?
R was a
5%. Okay. First step to solve this should be?
divided.
Yep. So I'll just reduce that. Well, I'm going to reduce that fraction. 5 over 100 is just 1 out of 20. So I'm going to write it that way. Okay. Next step.
You take the natural log.
Excellent. Yep. Remember, if we're solving for time in one of these compound interest formulas, whether it's finitely many compounds or continuously compounds, we're going to need to use a log. The log in this case we need is the natural log. And last step would just then to be multiply by 20. And I get about 9.71 years. You know what? We're going to just stop here. This is the better place to stop.
Yes.
All right. So at this point, you guys should be able to do up to 150. So I think we left off at 138 last time. Boyd,
Yeah.
you had a homework problem you still want to talk about.
Yeah, I appreciate you remembering.
I know, it didn't look like you did. So I wanted to make sure we came back to it.
I 127, please.
127, sure thing, boss. All right, let's see here. It's this one. All right. So here we're solving a logarithmic equation. To do this, the first thing I'm going to do is condense it down into a single log. When we're condensing, the order that we do is we do power, and then product, and then quotient. So the first thing I'm looking for is a power property. I do see a power because I see a coefficient on my logarithm. So that coefficient of 1/2 is the same thing as an exponent of 1/2, which is the same thing as a square root. So I'm just going to write it as a square root. There's no product properties because there's not two logs that are being added. But there's a quotient property because I see the two logs being subtracted. So that gives me this. Now to cancel that natural log, what do I need to use? Exponent base of e. So the e just cancels the natural log. So on the left I have x plus 3 over x. And on the right I have e to the 0, which is 1. So what I'll do next is I'm going to treat this like a proportion and just kind of cross multiply. So I have square root x plus 3 over x. To get rid of the square root, I have to square both sides. And then we'll move everything all onto one side. And now I'll try to solve this quadratic. To solve this quadratic, I could either use factoring or the quadratic formula. I might be tempted to try to factor this because the leading coefficient is 1. However, I don't see two things that multiply to give me -3 and add to give me -1. So I'm stuck using the quadratic formula here, and that's okay.
Okay.
That can happen. Okay. So when I simplify this thing down, I get 1 plus or minus square root 13 over 2. But
You gotta check.
I gotta check. So I'm gonna actually write this as two separate ones, one with the plus and the other one with a minus. Now, it might be helpful here to decide whether these things were positive or negative. So if I just go ahead and type this into my calculator, I get that guy's 2.3. If I go back to the original problem, if I plug 2.3 into this log, it's positive. In this log, it's positive. So that answer is certainly okay. If I look at what I get when I do 1 minus, I get a negative number. If I plug that into the first log, negative 1.3 plus 3, that's okay. But if I plug it in the second log, no bueno. So this guy is bad. That's extraneous. But the first one was A-okay. We'll stick with him and keep him. Seems like a pretty good dude. Again, and if you wanted to check, you could absolutely check. If I do 1/2 times the natural log of that answer plus 3 minus the natural log of that answer, I get approximately 0, right? Negative 9.11 times 10 to the negative 11th is basically just 0. Why didn't it come out dead on? Because I used the rounded decimal rather than like an ants or like the entire expression. But like to me, I look at that and I go, that's 0. You know, if I have a times 10 to the negative and then it's a double-digit number, that's 0 to me. Close enough. Especially if I know I'm using a decimal approximation there. Okay. Boyd, you happy?
Yeah. For 128,
Mm-hmm.
so it's basically almost the same formula as 127, but the
Mm-hmm.
you would do it the square root of x plus 4. Would you like put the square root over the whole back fraction or only the denominator?
Only the denominator.
Okay.
Yes. Great, important question.
Good question.